Thank you, Mr. President. I want also to thank all the jury members for their presence today and for the time they have devoted to evaluate my work. Hi and welcome everyone. My name is Amine Kerchouche, and today I'm very pleased to present my PhD work entitled Regression and Reinforcement Learning Based Video Encoding Improvements. This work has been carried out at Interdigital with the collaboration of IETR Lab under the supervision of Franck Galpin, Thierry Dimon within Interdigital, Lu Zhang, and Daniel Ménard within IETR Lab. To begin with, let me just give you a bit of context on why video compression remains such a critical topic today. Over the past decade, we have witnessed a huge explosion in video traffic, which has tripled from 2017 to 2022, according to Cisco's forecast. And video now accounts for over 80% of all internet traffic worldwide. And this trend is only accelerating. One of the reasons is the rise of video streaming platforms, which deliver high-resolution video content to billions of users every day. In parallel, video characteristics have evolved dramatically. For example, the move from standard definition to high definition, and now the ultra-high definition. The frame rates also increased, reaching up to 120 FPS, and the bit depth also moved from 8 to 10 and more to support HDR and wider color gamut. All this puts a huge strain on the bandwidth and the storage, and that's exactly what makes efficient video compression essential. Just a quick recall on how video codec works. First, we have the video source that is fed to the encoder, where we are going to do some encoding steps to result in a bit stream. This bit stream is then stored or transmitted. At the other end, the decoder will receive this bit stream to do the inverse encoding steps and reconstruct the video sequence. What's important to note here is only the decoder that is standardized, letting more flexibility at the encoder side to develop and introduce new tools, whereas we can increase its complexity. And over the past decades, we have several standardizations, and the final standard called VVC or H266 was the latest one finalized in 2020 under the joint work of ETUT and MPEG groups. And VVC is the main focus of this thesis. Before digging into the VVC diagram, let's bring the YUV format, which is the main use in video compression. So a YUV frame consists of 3 channels. We have the Luma channel and 2 chroma components. In practice, the Luma channel carries the most perceptual and structural information of the image. And for this reason, we are going to focus only on the Luma channel in this work. And the Luma channel is the input of the VVC diagram, and the first step is the partitioning. So the encoder takes the Luma channel and divides it into blocks called CTUs or cutting tree units. Then it does a recursive splitting for each CTU to result in smaller blocks called cutting units or CUs. Then the next step is prediction. So we can use the spatial information by using the entropy prediction, or we can use temporal information within the previous decoded frames and its entropy prediction. And in this work, we are going to focus only on the entropy prediction. So for each scanning unit, we are going to calculate its predicted entra block using the entra modes right here. Then to continue the rest of the VVC diagram, let's make ourselves at this encoding time step where we are taking this red block here with its associated entra predicted block. So we have the original block and its entra predicted block. First, what we do is subtraction of these 2 blocks to result in a residual. This residual is then transformed to decolorate its signal into few coefficients. Then we can quantize this transformed block into fewer coefficients, and then this quantized block is entropy coded to result in the bit stream. At this stage, we can get the rate value. Then if we do the decoding steps, we are just going to do the inverse encoding steps, starting by the inverse quantization, then the inverse transform, and here we can get the reconstructed residual. We add the entra predicted block, and we get the reconstructed block. Here we can apply some in-loop filters to enhance the artifacts and the error. And at this point, we can calculate the distortion between the reconstructed block and its original block. And using this distortion, we can calculate the final rate distortion cost that equals to the distortion plus a lambda multiplied by the rate. This lambda right here is a balancing factor, and it's directly related to the quantization parameter used during encoding. This rate distortion cost is calculated during a process called rate distortion optimization process, which is the core of video encoding, where the encoders tries a combinatorial or combination of parameters and try to find the best combination that minimizes this rate. So these encoding steps are done in nested way, meaning that for each partitioning mode, we are going to test combination of predictions, and for each of those, we are going to test, for example, different options of transform, making the problem highly combinatorial. As quite simply, the more candidates we have, the more complex rate distortion optimization becomes. So to see this explosion in candidates, here we can compare, for example, the VVC, the latest standard, with its predecessor, HEVC. For the partitioning, for HEVC, for example, we have two partitioning mode only. So whether we let the block as it is without further splitting, and it's the no split mode, or we use the quad tree, which divides the block into 4 equal sized non-overlapping sub-blocks. Whereas in VVC, we introduced the new tool called MTT, or multi-type tree. So in addition to quad tree and no split, we have binary tree and ternary tree. For binary tree, it divides the block into 2 non-overlapping sub-blocks in horizontal or vertical direction. And for ternary tree, it divides the block into 3 non-overlapping sub-blocks with a ratio size of 1:1, and for both horizontal and vertical direction. So here we have 6 possible modes instead of 2 as in HEVC. To have an example right here, let's take this 64 by 64 cutting unit. And in HEVC, for example, we can do only a recursive splitting using quad tree, or let the block as they are without further splitting, right? Like so. And for the VVC, for example, so first for this 64 by 64, we can do a quad tree. And if we focus on this black box right here, we can do nested entity using binary trees or ternary trees to adapt more to the structure of the block. And for example, if we do a full evaluation of on top of this 64 by 64, we can end up with 341 evaluations using all the partitioning possible. Whereas for the same scenario in VVC, this number increased to 721,000 evaluations, which is an increase of about 2,000 compared to HEVC. To have a concrete example, here an original frame that I'm going to encode with HEVC, and I will plot the resulting partitioning tree on top of this image. Then I will switch to the VVC to see the difference between the two. So here we use the entra prediction at this quantization parameter, and we got this quality right here. And for example, if you focus on the flowers right here, we have more quad trees to adapt more to the structure of the image. And then I will switch to the VVC partitioning for the same quality, and we get this partitioning here. So you can see that we have fewer partitioning, but at the expense in encoding, we have more combinations to test to find this kind of partitioning that is more adapted to the structure of the image. And this is for partitioning. And as I said, we are going to focus on the entra prediction. And here in blue are the introduced new tools of entra prediction in VVC compared to the red one, which are the HEVC prediction modes. And here we can increase, for example, approximately about 4 the complexity compared to the HEVC. And also for the transform step, here we have more options to test compared to the HEVC, where we have only one, plus the new tool LFNST introduced in VVC, which is also approximately about 4 that we can increase the complexity of the transform of VVC compared to HEVC one. And then we quantize and do the rest of the encoding steps. And this is an exhaustive search space to find the best combination that minimizes the rate distortion cost. To use and using this exhaustive search, we can end up, for example, with this kind of comparison, where I use different VTM versions. The VTM is the VVC test model, and I compare it with the HM, which is the test model of HEVC, using 3 configurations, including all entra, random access, and LDB. So for all entra here, we are using only the entra prediction for full frames. And for random access and LDB here, we can use some temporal predictions. And if we focus, for example, on the blue curve that corresponds to the all entra configuration, Here in the y-axis is the relative encoding time to HM. You can see we can increase, or the complexity is about 28 times of the encoding time of HEVC, with a compression efficiency about 27%. So the goal or the thesis aims to reduce the encoding complexity, especially at the encoder side. And one of the promising results is, one of the promising lead is the partitioning. So here we can see that we can increase by about 2000 if we do a full evaluation, and it's also the top of the RDO process. So for example, here we can do an early elimination of unnecessary splits, for example, and select a subset of splits to be evaluated by the RDO process and continue the rest of the encoding steps. By doing this, we can lower the complexity of the encoder. And in the state of the art, there are a lot of partitioning acceleration techniques, and we can categorize them into handcrafted techniques based on simple rules. We have also machine learning, traditional machine learning techniques based on SVM or random forest, and we have deep learning techniques based on classification, regression, or even reinforcement learning tasks. And here, for example, I plot the partitioning acceleration techniques proposed on top of VTM version 10.2 here. And the default point here of the VTM corresponds to 100% of encoding time with a 0% BD rate loss. The BD rate here is a complexity metric, here a metric that measures the compression efficiency of, for example, two techniques. And this MTT tree corresponds to MTT depth, which is 3 here in default VTM, which represents the number of nested binary trees or ternary trees done after a quad tree. And this acceleration techniques here, you can see that generally they propose one single trade-off of encoding time and BD rate loss, and they compare these points here with the default points of VTM. But if we dig, for example, in the default VTM configurations, we can end up with this curve right here without any acceleration by only setting the MTT depth, for example. Here, that the meaning of the MTT depth, for example, the MTT1 corresponds of doing one binary tree or ternary tree after quad tree. Same thing for MTT2 by doing 2 depths, and the default point corresponds to do 3 depths of binary tree or ternary trees after quad tree. So the goal here is to be on the bottom left of this curve, and you can see that the majority of state-of-the-art techniques are not good compared to this default curve right here. And this is only for VTM 10. I plot here different VTM versions, and each time I plot alongside the partitioning acceleration technique proposed on top of these VTM versions. A direct comparison is not always fair to do, because here we are depending to the encoding time for each VTM version. For example, if you see this right figure right here, where I plot different VTM versions starting from VTM 3 to the latest one, VTM 23.11. So each time, whether we optimize the implementation or introduce new tools. So using the encoding time to compare with state of the art, it's not always fair. So to mitigate this issue, we propose a new evaluation methodology. And in our old test, we are using the common test condition sequences proposed by GBET in all Entra configuration. And for this, we are keeping the BD rate metric that measures the compression efficiency between, for example, the default VTM curve with our proposed techniques. And the issue here is the encoding time, which is VTM specific and depends only on the implementation. So to mitigate this, we propose our own complexity ratio, which calculates a ratio between the number of cumulated pixels through the RDO process of default VTM with the number of cumulated pixels through the RDO with the VTM plus the acceleration technique. And in this figure, you can see I plot alongside with the default encoding time curve in gray, the complexity ratio curve. And you can see that there are a big similarity between them. But for example, if I change the hardware environment, the gray curve of the encoding time may change its position because it depends on the time. So this is why we are using this complexity ratio, and we made it available on the public GitHub of Interdigital to make the state of the art compare with us. And for this, we are proposing 4 contributions. We have a survey that got accepted 2 hours before, and we have 2 regression contributions and 1 reinforcement learning technique. And for lack of time, I will present one regression contribution and one reinforcement learning. For this, I will follow this overview. First, I will present the regression technique, then I will pass to the reinforcement learning one, and I will conclude and give some perspectives. Starting by the first contribution called NN-based regression for RD cost approximation in VVC intra-block partitioning. Here we got a problem. So the most majority of state-of-the-art technique model the partitioning as a classification task. For example, for a coding unit, a model is trained to predict class probability. And this doesn't allow well with the split partitioning process, which is based on rate distortion cost optimization and not class probabilities. To better illustrate this, I propose this figure right here, where I plot the evolution of rate distortion cost curves for each possible partitioning mode for a given 32 by 32 block across different quantization parameters. And all these curves are relative to the blue one, which is the rate distortion curve of the no-split mode. And here you can see that we have three regions. So note that the lower curve, the better partitioning mode is. For example, in this area with this range of quantization parameters, the quad tree curve is the lowest, which means that the quad tree is the best and optimal choice to do for this 32 by 32 block. And for this range, or the second area, this range of quantization parameters, the binary tree vertical is the best choice so far. And for highest quantization parameter, the no split becomes optimal. Here you can see that there is a relationship and relative understanding between the rate distortion cost or the evolution of rate distortion cost across encoding parameters. So instead of doing a pure classification as the most majority of state-of-the-art techniques, we can directly regress on this rate distortion cost. And to address this problem of regression, we propose this framework that operates at the CU level. So for each coding unit, we are extracting some information, and this information are fed to a neural network that predicts rate distortion cost for each possible mode. Then these predictions are fed to a selection module that identifies a subset of partitioning mode to be evaluated on the rate distortion optimization process. And our goal was to handle different CU sizes within a single neural network. And for this, in this table here, I report the number of block evaluations for each CU size. So by doing the entire partitioning modes configuration on top of each CU level. And the highlighted values here corresponds to the highest number of evaluations per CU size. And for this reason, we're focusing on these 6 CU sizes right here. And also we want to treat these CU sizes using one single neural network to lower the memory footprints instead of training one single neural network per CU size. But here, how can we handle these different inputs using one single neural network? The solution for that, for example, we can project all the CUs into one-dimensional feature vector. And this feature vector can be representative to any CU that we can handle here. And consists of 4 feature sets, including the neighboring information, parent information, block information, and spatial information. So to see the details of each feature set, for example, the neighboring information here, we know that in video encoding, the encoding order is done in raster way. So making the top and left coding blocks of the current block being encoded available, which have already undergone their encoding process. So we can extract some information and use them as input for our feature vector here. And for example, we can use the best rate distortion cost found on the top and left coding blocks, and we normalize them by their sizes. We can also take the quad tree depth of each of these neighboring blocks, which corresponds to the number of nested quad tree done starting from the city root until reaching the neighboring block here. And then we can normalize this value by the maximum quad tree depth in VVC, which is 4. And for the parent information, know that in the partitioning tree for each CU leaf, we got a parent leaf. So for each CU, we have a parent CU. And for this, we can extract some information from the parent of the CU being encoded here. And for this, we take the cost of the no split as we allow it in our work because it's not that complex. And for this, we can take its rate distortion cost of the no split of the parent normalized by its size We also separate the rate and the distortion of this cost, and then we normalize them to use them as parent information. And for the third feature set, we use the block information. So for this, we take the width, the height of the CU normalized by the maximum CU size in VVC 128, and also we take the cost of the node split as we allow it, normalized by the size of the CU. We also separate the distortion and the rate of the node split, and we take also the quantization parameter used for the CU normalized by the maximum quantization parameter in VVC, which is 64. And for the last feature set, which is the spatial information, here we divide the block into 2x2 grid, and for each region, we calculate the hog histogram of oriented gradient features plus this GLCM information. And also we take 4 rows and columns causal pixels of the current CU in top and left block of the block, and for each region, we calculate also this hog and GLCM information. Then we concatenate all this information into one feature vector that will be the input of our neural network. And then the neural network consists of only 3 fully connected layers with a final output that predicts rate distortion cost for each possible mode. And the neural network contains only 100,000 parameters. And then the predictions are used by a selection module. So note that, as we saw in the state-of-the-art techniques, they propose generally one single trade-off. And to mitigate this and to have a broader range of trade-offs, we can use this module right here. And as we are predicting interpretable values, which are rate distortion costs, for example, we can use the top n minimum predicted rate distortion cost to control the complexity. And also, as the distance between this predicted rate distortion costs are kept, we can use a threshold t to control the quality of our prediction. So using these 2 parameters, we can have more than one trade-off and have a broader range of complexity and bit rate loss trade-offs. We trained our neural network using the BVI DVC dataset, which consists of 800 sequences, 200 for each of these 4 resolutions, and we used the VTM18 to encode them using these quantization parameters, and we end up with 95 million balanced samples. And during the training, we got a problem. So here I plot in this table the forbidden splits in VVC for each CU size that we treat. For example, this 32x8, which is a rectangular block, and in VVC, we cannot do a quad tree on top of this block or a ternary tree in a horizontal direction. So to mitigate these issues and remove the unwanted values from the training process, we can use a masked and balanced mean square error. And for this, for example, we can use this kind of masks, and we have a value 1 for wanted values and 0 for unwanted values. And we can use this mask in when we calculate the mean square error for one simple, and also a balancing factor which equals to the number of outputs divided by number of valid outputs. And then this balancing factor can be used in the overall mean square error. And thus, we can eliminate the unwanted values for the forbidden partitioning modes. For the results, as I said, we are using the complexity ratio versus the BD rate loss. And here I plot in black the default VTM18 that we used for training, and here we are testing on the CTC sequences. And in gray dashed line here is the VTM 10.2. So here you can see that we can already compare all together in one figure using this kind of evaluation methodology. And here, a state-of-the-art technique proposed by these authors right here, and the corresponding curve is the red one. So we use this technique because we had access to their code, and we integrate our complexity ratio to be able to compare with them. And also, the orange one here is one of our previous technique, which corresponds to a CNN that takes as input of 32x32 luma pixels plus the quantization parameters, and we predict rate distortion cost for each possible mode. And this state-of-the-art technique consists of multi-stages framework that takes 64x64 luma pixels, and using a CNN, they predict a mapping vector, and then they use for each sub-part of this predicted vector, they use multi-classification for each CU size to predict the class probabilities. So the first one is a size dependent. So we cannot be scalable to the CU sizes, and we can treat different CU sizes. The second one is a multi-stage that uses different stages to do a prediction. Then we mitigate all these issues by proposing a single stage using one single neural network that is independent of the CU size and predict weight distortion cost at once, and then select a subset to be tested on the weight distortion optimization process. And here we got the green curve right here, which has a broader range of trade-offs instead of single one across all the default VTM configuration. To conclude this contribution, we successfully reformulated the partitioning problem as a regression one instead of classification task. We used for this framework a single neural network that is independent of the CU size. We also, the framework enables us to have multiple trade-offs instead of a single one as used by state-of-the-art techniques. And also we have some limitations. So in particular, relying on the best trajectories found by the VTM using static dataset may limit the model generalization and adaptation to unseen scenarios, for example. And the second limitation here, without modeling the nature of the split decision process in video encoder, the decisions across partitioning depth may lack consistency. So let's take these limitations and move forward with the next contribution called reinforcement learning-based RD cost approximation for VVC intra-partitioning. So to mitigate these limitations, we need new motivations. First, we can frame the partitioning as a sequential decision-making problem. For that, we can use, for example, an interaction or an environment that is a dynamic, and that consists of optimal and suboptimal trajectories. And then we can learn a model that interacts with this environment and can select the best trajectory so far. These trajectories are selected based on, for example, their associated weight distortion cost. And to solve this problem, we can solve it using reinforcement learning algorithm, for example. And the new paradigm of training becomes like so. So we have a dynamic environment that generates states. These states are received by a DQN agent, which is an algorithm of reinforcement learning. And then the agent will take actions. And then based on these actions, the environment will reward this agent. And if we project this paradigm on our task, the environment will generate the input feature vector that we spoke about it earlier, and the agent will receive this states, and the actions are the possible partitioning mode. And the reward signal is only the associated weight distortion cost of each possible taken action. And here, as the partitioning process valid the Markov property that states that the future state depends only on the actual state and the actual action. For example, for a CU, the generated sub-CUs depend only on the actual CU and the action applied on this CU. So we can apply reinforcement learning on top of the partitioning process. And to simulate the training of our DQN agent, first we have a dynamic environment which consists of two partitioning depths, including 32 by 32 CUs, and the subsequent partitioning depth, including the resulting sub-CUs for each possible action here. And first, the model receives the first state, that is the first feature vector here, and we fed it to the decaying agent. We predict p-values, which are the rate distortion cost of each possible action. Then, based on the minimum, we select the next trajectory, which corresponds here, let's say, the binary tree horizontal. Then the next states are the sub-CUs generated using the binary tree horizontal. Then, for each feature vector, we also fed them to the decaying agent. We predict rate distortion cost or the q-values for each state. And also, we base on the minimum to select the action. And here, we just do the prediction using two partitioning depth. And note that this reinforcement learning algorithm allows the model to capture the interdepth dependencies and can be coherent when transiting between this partitioning tree, between this partitioning depths. So to achieve this interdepth loss or the interdepth dependency, I will use some formulas right here. Starting, or before that, we extracted this dynamic environment using the VTM. So for this, we have the actual ground truth selected by the VTM. So let's say the action selected for the first state here matches the selected action by the VTM, which is binary tree horizontal. And for the second state, let's say also it's a good action that matches the first state of the second depth. And for the next one, which is bad action that doesn't match the predicted values by the decaying agent. So to mitigate or to capture the inter-depth dependency between these two partitioning depths, the first formula here is used by the encoder, which is the formula used to calculate the cost of any partitioning mode, which equals to the sum of the minimum costs of the subsequent level plus a delta cost of actually signaling the splitting question. And if we apply this formula using the ground truth or the generated with distortion cost by the VTM, the cost of binary tree horizontal equals to the sum of the minimum cost of the subsequent level that corresponds to the no split for the first state and binary tree vertical for the second state, plus a delta of cost actually signaling this binary tree horizontal. And to use this formula also based on the actions of the agent, the new cost of binary tree horizontal equals to the cost of the no split for both states. But here, instead of taking the actual predictions of the agent, we can base on the action of the agent, but we select the actual ground truth of this value right here. So the cost, the cost equals to the cost of the both no split modes for these two states, plus a delta cost the same as the previous one. Then in general reinforcement learning algorithms, we do not have this ground truth. So how can we calculate the target and use it to calculate the mean square error? Here we can use, for example, the Bill-Ban formula, which allow us to calculate the target value, which equals to the actual reward plus the minimum of the next, the Q values of the next states, multiplied by gamma, which is a discount factor to take the impact of the next actions. So if we project this Feynman formula in our task, we will find that the target corresponds to the cost actually calculated based on the agent's action, and the reward corresponds to the cost of signaling actually the split, and the impact of next states corresponds to the sum of the minimum costs selected in the subsequent level. And gamma here corresponds with or equal to 1, which here means that we are taking the impact of the entire action of the next states. Then we use this target here with the Q value actually predicted in the first step to calculate this mean square error. And if we apply this on our task, we will find that we can calculate this mean square error between the cost actually predicted on the first step minus the cost actually calculated based on the agent's actions. Then this mean square error allows the model to capture and reduce the or increase the covariance between the decisions done when transiting between partitioning depths. So this is for the first mean square error, and also we use two other mean square error. The second one reduces the error between the predictions and the ground truth of the first depth, and the third mean square error reduces the error between the predictions and the ground truth of the second partitioning depth. And then we use this 3 mean square error into one single loss that takes all this mean square error using alpha factors to balance these errors. And for the results, we obtain this blue curve right here, where I zoom around the B point here. You can see that the decaying agent is capable to have better results than doing only a pure regression on the best trajectories. So note that this reinforcement learning agent was trained on optimal and suboptimal trajectories, and yet it achieves better trade-offs compared to a pure regression. And also we did an ablation study to see the impact of this interdepth loss. We remove it from the training of this reinforcement learning agent. We got this red curve right here. So we see that the interdepth dependency is crucial for our reinforcement learning agent to get the blue curve that contains this mean square error. And to see a concrete example right here, I have a Luma channel, and on top of it, I plot the matching partitioning in blue between the VTM and the reinforcement learning agent. And in red are the partitions found by the VTM, default VTM, and not by the reinforcement learning agent. And the orange partitions are the partitions found by the RL agent and not by the VTM. For example, if I zoom in these areas right here, you can see that the VTM can find, for example, this partitioning right here, which is adapted to the structure and not by the reinforcement learning agent. Same thing for this partition right here, which is more adapted to the structure, which is a binary tree in a vertical direction, and the agent took a horizontal direction, which is not adapted to the structure. We dig into this problem and we found that we can maybe introduce new feature at the input vector. And for this, we have a parameter called split series, which is written in 64 bits, which can be represented in decimal and also in binary. And for each 5-segment bit, it gives us which partitioning mode was done on which partitioning depth. So for example, if you see this partitioning trees right here, starting from the CTU until the top or the left block, it gives us the splits or the series of splits done from the CTU until reaching the top or the left blocks. So we use this split series in the neighboring information. We retrained the reinforcement learning agent, and we got this new result here. So you can see here that now we have matching partitioning in this area, and also we successfully have a partitioning that is more adapted to the structure and matches the VTM default partition. So for the result, we get this new curve here, which is so far the best compared to the previous contributions and also the state-of-the-art techniques. We also did some tests using different VTM versions. So for each of these VTM versions, including VTM 10 and the latest one, VTM 23.11, we include our reinforcement learning agent, and we can also get some trade-offs compared to default VTM version right here. And also we can compare all together using our methodology metric. We also use different test sets, including, for example, the call for evidence sequences in random access configuration, but using only the first entry frame, and yet we can have some trade-offs compared to the default one in VTM. We also use unseen quantization parameters, which are different from the training quantization parameters that we used 22, 27, 32, 37, and here we are using unseen quantization parameter to see how can we generalize to this quantization parameter, and yet we have better trade-offs compared to the default VTM. We also did calculate the time overhead of our framework. So for this, we use two environments of testing. We use the CPU generation 2019 and CPU generation of 2024. And for each, we have 3 columns. So we have the NN overhead, the input overhead, and the overall framework overhead. So note here, we run our framework without applying the acceleration impact. So to see exactly how or how much the overhead is for our framework. So for the generation of 2019, we got, for example, 8% of the NN overhead. And for the second test, we got, for example, 3%. And note that these tests are done using the same implementation for both. And for example, the entire framework, we got in the first test 18%, and for the second one, we get 10%. So you can see here that the encoding time isn't always fair to use it and evaluate this kind of work that relies on the rate distortion optimization process. So to conclude this second contribution, we effectively leveraged the sequential nature of partitioning process using deep Q-network algorithm to solve this problem. And the agent is capable to reduce the RDO evaluations and also can get competitive trade-offs. Also, the design of this reinforcement learning agent is size independent and can treat different CU sizes and different partitioning depths. To conclude and give some perspectives, here we successfully developed partitioning acceleration techniques in VVC using either regression or reinforcement learning approaches. And both of these contributions are size independent and can treat different CU sizes using a single neural network that to lower the memory footprints. And also we validate our contributions using extensive evaluations, for example, using different VTM versions or different test set or even unseen quantization parameters. We also showed that the importance of this rate distortion cost can be used. For example, we are predicting interpretable values, and we can get range of trade-offs instead of a single one using, for example, the top and minimum or a threshold T. And we also successfully solved the sequential decision-making problem using reinforcement learning algorithm. So for short-term perspectives here, as we saw for the results, by simply introducing new features, we can get better trade-offs. So here I will let the investigation open for further inclusion of new feature set to maybe get better trade-offs. We also can validate the portability of our contributions using alternative encoders, for example, Vivian instead of the VTM versions. Also, we can use or explore the parallelization of our framework that is a single thread implementation and can, for example, reduce or eliminate the overhead of the framework using dedicated engines like NPUs. And for the long-term perspectives, here we saw that by integrating this reinforcement learning agent with the conventional encoding process, we can get better configuration or better trade-offs. So here we can merge these agents with the conventional encoding process for the future or the new hybrid codecs, for example. We also can explore, for example, the live training. So here we extracted the dynamic environment from the VTM by encoding sequences. But here, for example, we can include directly the reinforcement learning agent, which is ready to do because our reinforcement learning agent or the error algorithm is adapted to this kind of scenarios, and using the reinforcement learning agent inside the VTM and try to do the training inside the VTM, for example. We can also, here we did a prediction of rate distortion cost. For example, we can separate the rate and the distortion, for example, and we predict these values to, for example, solve other problems like rate control. So here I will let you with our list of publications, and this is it for me. Thank you very much for your attention.